turn recording on now, and I'll just go over this quickly so anybody that's going to tune in later on will hear this also. The exam, you'll have 2 shots of the exam. It will not be timed. It'll be due for sure. You got to get it in on Wednesday by end of day, because shortly after that I have to start entering grades. And you'll do it on Blackboard. You'll have to use Firefox as your browser because the other browsers are not stable with the exam function in Blackboard. You have 2 homework assignments. It's actually one homework assignment split into 2 parts. One has a chi-square problem. The other has a correlation problem. You'll need to use SPSS for both of the problems. And in that vein, we have one more class which is required on site. And because of scheduling issues and a lot of people that are starting vacation or maybe out of town next week, I am suggesting that you come to either the Monday class or the Wednesday class. You do not have to tell me which of the 2 that you're coming to. During those classes, I'll give a brief session on multiple regression. It's not a required part of this course, but it's an important tool in statistics and public health statistics. So it's something that you're going to want to learn about. During the remainder of those sessions, I'm going to be working with some commonly available databases that you can download. A lot of them are very large databases, NHANES, the New York City Community Health Survey, which just takes place every year, and a couple of others. I think some of them are actually available now. You can see them in the folder for next week's assignment and next week's classes. So I'm going to work with those and hopefully have you work with them on the computers as well, so that you get an idea of when you are confronted with some data or study that you're working with, how you might approach deciding how you're going to analyze it statistically, what tools you're going to use, and what the results might be that you might see as you do it. So on those 2 days, you'll be able to work with me on a lot of these things, and I'm hoping that that'll cement this material in your mind so that when you go on and take EPI, you don't get into a situation where about the middle of the semester, the instructor says, oh, and you guys, you did chi-square when you took statistics, and you guys all give them a blank stare, and then they come back to Tony DeVito and they say, Tony, why didn't you teach them about chi-square? So hopefully that'll avoid a little bit of that, because we'll get a little bit of exercise in actually applying this stuff. Now, I will, if you want, you don't have to listen to me drone on during those 2 days for the whole time. If you want, you can actually work on the homework here. I know a lot of you guys have issues with access to SPSS and so on and so forth. You can work either in this room, and I know C008, the room next to us, is frequently empty, so you can probably use the computers in there as well. You can also, if you wish, again, if you're having issues with SPSS, work on the exam here. Now, the only caveat is that if you're going to work on the exam, you have to work alone. You should really go into C008 and don't confer with other students while you're working on the exam. Homework's no problem. You can confer with the other students. You can work together on the homeworks and help each other understand this stuff. You can ask me questions and so on and so forth. But on the exam, you're going to have to work on your own. So I'm hoping that that's the fairest way that I can think of to end up the semester and make sure that we cover all the material, and also give us a chance to really kind of put it all together as well. Okay, so if you want, you can email me if you think that you have suggestions, you have any issues with that. Now, if anybody has decided that they might want to do a presentation, they have their own data that they're working with and might want to do that, I'd appreciate it if you would let me know by Friday. If you have Thursday, end of day if you're not going to have accessible by email over the weekend, or Friday end of day if I can still get to you by email over the weekend. Let me know that you're going to do that, and email me the type of data that you're going to be working with, if it's a small data set, what the data set has in it, and maybe some of your preliminary work on descriptive statistics and what direction you're going with it, so that I can critique it a little bit, give you some feedback before you present it next week. And in that case, I would appreciate knowing that you want to present on Monday or Wednesday. Those of you that are just going to turn up in the class to finish up on Monday or Wednesday don't have to tell me which day you're coming. But if you want to do a presentation, let me know so I can be prepared with the materials that we need, the poster board and the stickers and stuff like that, for you to set up a display. So let me move on to linear regression and correlation. Yes.
For the plan, is it only it's no chi-square?
Yeah, it's not cumulative. It'll only be chi-square, odds ratio, relative risk, and correlation and regression. Just what we did last week, just what we did on Monday, just what we're going to do now. It will not include the multiple regression, which we're going to talk about on Monday, and that I'll demonstrate on Monday. But you're not going to have a homework or any exam material on that. Yeah,
the last exam will cover correlation and regression.
And chi-square. It should be chi-square. Oh yeah, I'll fix that. Yeah. It's going to be correlation regression. Is that the last announcement I put up? I'll make sure I fix that. Okay, yeah, there's no time limit. The 3-hour time limit is out. You have as much time as you need. Save your answers so you can go back to it again. Don't save and submit until you're done. The first time you save and submit, you'll have feedback on which ones you got wrong. You'll get another shot to do it, but you only have 2 shots. Okay, so and I think you should do the homeworks before you attempt the exam, because the homeworks will inform you on the kind of materials that we're talking about, give you a little practice with it as well. And also on Monday, I'll be here and I can answer questions on the homework as well and on those topics. Okay, so let's talk about regression, correlation and regression. This is one of those places where one of these 2 words has real meaning in terms of like common conversation. Correlation, right? We talk about that all the time. There's a correlation between this and this and that, right? But the other word has an uncommon usage in a regular language and is very different from what we use it for in statistics. Regression. There's the source of that. I'll go into a little bit of the source of that word, but regression is doesn't really give you a very good description of what that statistic is all about. Okay, now I have some documents on here. I suggest you do the textbook readings at some point. Chapter 7 is basically all on correlation and regression. There's a document, correlation regression intro. That's an exercise that we can work on. I'm going to open it up here. And I have a database there as well. And that database includes data. Let me just open up that Excel file. That database has 2 variables in it. And those 2 variables, if they ever show up, oh, here we go. Okay, let me blow this up so you can see it a little bit better. Okay, here we go. Those 2 variables, actually there's 3 variables there. There's the year that this data was taken. There is the price of a single slice of pizza that year, and the price of a subway ride that year. Okay, I think the first time I ever took the subway was probably around this time, and the subway cost 15 cents at that time, believe it or not. And since it was a nickel and a dime, they had to have a token, and it was a tiny, tiny little token. Right, some of you guys might have seen that. Sometimes it turns up in jewelry and rings and stuff like that. In fact, the MTA has a museum, subway museum, and New York City government has a little trinket shop down in Lower Manhattan, and you can actually buy these old subway tokens built into jewelry and stuff like that. So yeah, it was 15 cents. They had a small token. Then they went to a quarter, late 60s or something like that, and they didn't use tokens because you put a quarter in, and then they went to 35 cents and had to go back to a big token with a big Y in it and so on. And then by the time they got to $1, they went from that point on, things started to go towards these magnetic card readers and stuff like that. I don't remember exactly when they came in, but I think it was like late 90s or something like that. Yeah, maybe around this time or something like that. Well, there are people that have a notion that the price of a slice of pizza in New York City somehow or other is by the cartel, by the pizza and subway cartel, is fixed so that the price of a slice of pizza is always the same amount of money as it costs to get on the train in New York. right? So what I've done here is, as best I could remember and as best I could find on the line, you can actually find, go back and find places on various old New York sites where they talk about the price of the subway and how much pizza costs. But best I could construct is this table right here. So we got three variables. We have the year, we have the price of pizza, and we have the price of a subway ride. Okay, and my thesis is, my hypothesis is that there's an association between the price of pizza and the cost of getting onto the subway. Okay, and I think now it's actually, yeah, actually, I got this reversed. This was a 275. I didn't take the discount. And the price of pizza, I think you can still find this price of pizza for an average of about 250, I think. And this is reversed also. This should be 238 here. And 250. Okay, it was 250 in 2014. Okay, that's without the discount if you buy the multiple fare cards. So at any rate, so we're going to test this hypothesis. So we're looking for an association between these two sets of numbers. Okay, well, one of the things I can do, which helps a lot of times, is to display these numbers graphically. So I'm going to do this quickly and see if I can't do this with SPSS. Okay, I'm going to make a line graph here. There's a line graph, and let's see what happens here. Wow, it sure looks like as the price of pizza goes up, the subway fare goes up as well. Sure looks like there's a lot of association here, right? So I got two lines here. The blue line represents the price of pizza. The red line represents the subway fare. Let me see if there's another way I can display this. How about if I display it as something called a scatter plot? A scatter plot is something that displays on an XY coordinate on a graph. It displays the value for one variable for the year 1960. It displays the value of a slice of pizza as the x-axis and the price of a subway fare as the y-axis, and so on and so forth. And each one of these, this then represents x is 0.15 and y is 0.15. It's a point. It's a dot on a graph. Okay, and I'm gonna see if I can't do that now. Let's see, scatter plot. Okay, and there we go. There's our scatter plot. Okay, so now, interestingly enough, boy, this really looks almost like a straight line, doesn't it? If there is a perfect correlation between two numerical variables, in other words, as one goes up, the other one goes up exactly the same amount, this would be a perfectly straight line. So now this isn't a perfectly straight line, is it? It's close, but it's not a perfectly straight line. However, the fact that it's so close suggests to me that there's a high degree of association. Speaking statistically, I would call that a high degree of correlation between the price of the subway and the price of pizza. So each one of these dots represents the value. For instance, here, subway costs $1 and the pizza costs $1. Here, subway costs $1.75, pizza costs $1.50, and so on and so forth. In fact, I could actually draw a line that approximates this. A straight line goes straight through these things, right? So that I could actually create a formula for that line, which would show me the mathematical relationship between the price of pizza and the price of Subway. So that, for instance, if I didn't know what it was during the year 2007, I could guess at it by using that formula to fill in that missing information for me, right? Use that formula if I know the price of Subway that year, to fill in what the price of pizza would have been that year based on this relationship. Okay, so basically what I'm looking at here is trying to define how certain am I is that this is a real relationship, a real correlation, and not due to chance. Okay, well, SPSS is going to let me do that. Okay, and I'm gonna take this same information, and you know what I'm going to do is I am going to paste it into SPSS because I had those couple of mistakes on there, didn't I? Okay, I'm going to go here. I'm going to go open up SPSS. Okay, we wait for that to come up. Okay, and I am going to go in here. And well, I got a little bit of a problem there, don't I? The problem is that if I put it in here like this, it's going to appear to be paired data, right? Which is not what I'm after. Let me open up my original file. Open data. Okay, I really need it. Here, let me open this one up. I'll have to correct it. Oh, no, it's going to be the same way in here. Okay, let's see. Can I do this here? No, I think I'm okay here. Let's see. See if I can't do this. Analyze. Now I want to determine whether there is an association between these two variables. Okay, and again, notice in the beginning I did it graphically, didn't I? So I'm going to repeat that here. I'm going to go to Legacy Dialogues, and I'm going to go down here. One of the choices is a scatter dot. I'm going to click on that, and I'm going to say I want a simple scatter dot, and I'm going to define the variables that I'm interested in. And the variable for X is going to be the subway fare, and the variable for Y is going to be cost of a slice of pizza. Doesn't matter which one I use, because right now I'm just interested in seeing if it looks like there's an association, if these dots are all just scattered randomly, or if it looks like there's some pattern there, like one is associated with the other. And there's the same diagram, same graph that I just produced in Excel. Here's the price of a subway fare. Here's each one of these dots represents one of these pairs of data. And I'm not sure the data is exactly the same on here as the Excel file because I noticed I had to change a couple of those numbers. I'm going to stick with what I have here, though. It really doesn't matter that much. Okay, so now one of the things I can do in Excel is I can double click on this, and it lets me edit this chart. While I'm editing this chart, one of the things I can do is actually ask it to produce a line that is a best fit for all of these different values. Okay, and there's the line. If you look at this line goes very close to all of these different values, and there's a balance between the numbers that are above it and the numbers that are below it. In fact, this least squares line, what SPSS does is it draws a straight line so that the square of the distance between this point and the line, and this point and the line, and so on and so forth, equals the squares of the distances of all the other points on the other side of the line. It balances those squares of those different distances. Okay, and it picks out the number, it picks out the line where the slope and the point where it starts is the best fit to give you the lowest numbers for those squares so that they're balanced, and also balances them on both sides. So it creates this correlation line. And you can see that in this particular case, it seems to be a very strong correlation between, I can go out of this now. Seems to be a very strong correlation between the subway fare and the cost of a slice of pizza. Okay, now let's say we want to quantify that. Well, there is a statistic that we can use. We're not going to calculate it by hand, which summarizes all those squares, the size of those squares and the number of different points. I'm going to go to Analyze, Correlate, and Bivariate. Why bivariate? Because there's two variables. By the way, just let me ask you something. What kind of variables are we associating here? What kind of variable is the price of a slice of pizza? Numerical. What kind of variable is the price of a subway ride? Numerical also. So we now have a tool where we can see if there's an association between two numerical variables, right? When we were working with t-tests and analysis of variance, we were working with a numerical variable split up into different groups. Those groups that was a categorical variable for the groups and a numerical variable. When we were working with chi-square, we were working with two categorical variables. Odds ratio, two categorical variables. Now we have a tool to work with to see if there's an association between two numerical variables. Okay, so I'm going to click on bivariate because there's two variables here. Okay, I'm going to put in the two variables. And it's going to calculate something called a Pearson's correlation coefficient. That's represented by the letter R or letter rho, Greek letter rho. Okay, so let's take a look at what this is. Okay, so the Pearson's correlation. Well, they kind of SPSS does this kind of funky trick that it does very frequently, where when you're comparing two things, you see four results because it kind of looks at every possible combination. What's the correlation between the cost of a slice of pizza and the cost of a slice of pizza? The correlation is one, right? Well, because it's just, you're comparing the same thing. Same thing, subway fare and subway fare is one. But let's see how cost of a slice of pizza correlates with the subway fare, and it's 0.993. Interestingly enough, the closer this number is to 1, the the closer is the association, the better is the correlation between the two variables. So 0.99 is a very good correlation. And we could see that in the graph, that it's almost a perfect straight line. And how do we know that this correlation is not really zero, is different than zero, different than no correlation at all? Well, that's what our significance tells us. Our p-value or significance tells us that not only is this a strong correlation, but there's enough data and evidence here to tell me that there's less than a 5% chance of me being wrong if I say that there is an association. Okay, my null hypothesis here is that there's no association. My alternative hypothesis is that there is an association. So in this case, I reject my null hypothesis and accept my alternative hypothesis. And this is my quantity. This is the quantity tells me how strong the association is. So if I have a 0, there's no association. My chart would have looked like it's just a cloud of dots. There would have been you wouldn't have seen anywhere that would have made any sense to draw a line through. If my association is 1, it would have been a straight line. Anything in between, like if the dots were scattered here, here, but you could see a pattern to it, it might have had an association, correlation of 0.5. An association, but not a correlation that's as strong as the one that we see here, and not a perfect correlation. What do you think it would mean if the association were -1? Anyone take a guess at that? If the Pearson's chi-square value was close to negative, instead of being plus 0.993, it was negative 0.993, what do you think that might mean? What do you think the graph might look like? Anybody online want to take a guess at that? You got the right idea. It is it's just as strong a correlation. Exactly right. What you would see is that this line would be going downwards instead of upwards. What does that mean? That means that as the subway fare went up, the price of a slice of pizza went down, which would be a wonderful world, but it doesn't work like that, right? But that's the way we would describe a negative correlation. And there's plenty of situations where you come across negative correlations. The more of a antibiotic that you give, the fewer bacteria that are present in the bloodstream or something like that, right? So there are plenty of times when you'll see a negative correlation rather than about 99 cents. First of all, number one, let me say something definitively here. That dollar pizza, that 99 slice of pizza is not pizza. I don't know what it is. I've tasted it. I don't know what that stuff is, but it is not pizza. Okay, so at any rate, if we had a negative correlation, we see this pointing downwards rather than upwards. But how good the line fit, how good if it is to a straight line, represents how big that number is. It goes from +1 through 0 to -1. 0 being closer to 0 means not no correlation. Chi-squared homework says over. There's probably a date on there. I didn't change it. Didn't set up right. That's one of the reasons. One of the reasons it wasn't available is probably because I didn't get a chance to go back there and go through all the options. There's a million little options on there. You might have noticed there were like little triangles I had to click to point down and change 3 other options and stuff. Yeah, I'll go back there and fix that. Yeah, you should be able to still do it. I don't think it'll lock you out or anything like that. But I'll make sure that those dates are fixed on there. Okay, so at any rate, so that's what we're dealing with on correlation. I just want to see. I have my document over here. Okay, let's see if we go back to the Word document. If I can find it. Okay, so okay, let's see. That's why there is something in the homework I want to show you right now. Now that I'm on this topic, one of the questions on the homework. This I think is an opportune time to bring this up. Okay, here's a simple question on the homework. See if the charts appear. There they are. Okay. Now let's take a look at this. These are 6 plots that represent correlation between two numerical variables. Okay, so we know that if it's a perfect straight line, that the R value is, Pearson's R correlation value is 1, right? So what do you think A is? What do you think the R value for that one is? Well, you one, but what kind of one?
-1.
Negative one, right? Because it's sloped downwards. Okay. How about D? What do you think the correlation is there? There's our positive one, right? How about, and the choices are 0.5, 0.85, and 0. Okay, so let's see. If we're going to look at 0.5, right, it's going to be something. 0.85 is going to be very close to a straight line. Well, which is the one that's closest to the straight line? Looks like E, right? Looks as closest to straight. That's probably the plus 0.85. Well, then we're left with these 3 over here. Well, these 2, I can kind of see. This looks like a weak positive correlation. This looks like a weak negative correlation. So they're probably the plus 0.5 and the minus 0.5, right? So what does that leave us with over here for this one, which is just cloud of dots? That's probably the one that's closest to an R value of 0, right? So here it is, negative 0.5. There it is, point down there, negative. Yeah, moderate negative correlation. I guess this, yeah, this one over here. Yeah. So at any rate, that just gives you an idea of one of the first things you might do. One of the first things thanks for the answers online too. One of the first things you might do when you go through one of these examples is display the data graphically, so you can look to see if it's worth chasing a correlation between these values. Okay, so let me get back to this. Okay, so now the next thing I want to bring up is, let me go back to Word. Okay, next thing I want to bring up is that many correlations are not necessarily have anything to do with causality. When you talk about correlation, doesn't mean that one value causes the other value. I'm going to give you an example, for instance. Is there a correlation between the number of firemen that respond to a fire and the amount of damage from a fire? Well, what do you think? If a lot of firemen show up at a fire, do you think that there's more damage? Probably is.
Yeah.
There is, right? So there's a correlation between the number of firemen and the amount of damage that is incurred from the fire, right? Because a big fire means more firemen, right? Does that mean that the firemen are causing the extra damage? No, it's fire causing it. So there is a correlation, but there's not causality. It doesn't require causality. All you need to know is that there's an association. When we talk about regression, when we start to talk about regression, we're going to apply that to situations where we believe there is causality, where we want to examine, well, if we do this, how does it affect this other numerical variable? How much will it increase it? Can we predict how much it'll increase it? But as far as correlation is concerned, we don't have to worry about causality there. I'm going to I actually gave you a link here, I believe, if I left it in. I got to go back to sessions. I gave you a link to a website where this guy is kind of like, I guess he has too much time on his hands, I guess is really what the problem is. But he has a website where he tracks examples of spurious correlations. Correlations that are real, meaning that if you track it over time, there seems to be an association, but clearly one is not causing the other. So I'll show you a couple of examples of that. Okay. Okay. He claims that the more people eat cheese, the more people are killed by their bed sheets. Okay. And how does he demonstrate this? He actually collected data from mortality records. Let me see if I can find it here. Actually, I'll go to his website and show it to you. It should show up here also, but I guess, yeah, let me go to his website. That's the other link there, where you can actually see these charts that he's occurred. Suicides by hanging, strangulation, and suffocation, and U.S. spending on science, space, and technology. Okay, now there, it does look like there's a pretty good association there, right? Number of people who drowned by falling into a pool, and the number of films Nicolas Cage appeared in, year by year, right? Interestingly enough, now think what he had to do to find all this stuff. There we are. There's our tangled in bed sheets versus cheese consumption, per capita consumption of margarine, and the divorce rate in Maine. Now, my guess is that he tracked he managed to find data on the per capita consumption of margarine, but he had to like test the divorce rate in every state in the union in order to figure out which one to fit this graph the best. So obviously he's playing around with facts that are clearly not associated, but it's interesting that you can find spurious correlation. In other words, when you find a correlation, don't assume that there's a real association between the two variables, right? Because a lot of times it's easy to convince yourself that there is. And we see that all the time, right? When we hear about cancer clusters and things like that, people are concerned that something in their environment is causing the increased rate of disease in their community. And when if you analyze the statistics very carefully, that's actually predictable. It's predictable that there's going to be locations, zip codes, or communities or something like that that are going to have dramatically higher rates of some disease versus other areas, without necessarily being caused by the environment, just being caused by chance. In other words, just like some people at the casino hit the jackpot. Unfortunately, a bad jackpot, but same idea. So if you got a chance, you might want to go back there and take a look at this. So you can have spurious correlations as well. Okay, so I'm going to move on very quickly through this. We'll come back and take a closer look at this after we run through the video. I don't want to spend too much time so that we have a little bit of time afterwards to go through some examples. Let me go back to my Word document. I gave you another example of a association. Oops, that's Excel. Here we go. Okay, in this example, 10 patients between 30 and 60 years old were randomly selected from patients at a long-term care facility, and the data that was obtained was their age and their blood pressure. Okay, seems reasonable. There's some association between age and blood pressure. So let's take a look at this data. Okay, and I think I gave you a SPSS file. You could actually type these in if you wanted to. Let's see if I have this here. Oh, I have it on black. I believe it's on Blackboard, but I'm going to see if I can't just type it in. So I don't have to go back there. Oh, okay, I think I got away with it. Let me clean this up a little bit. Okay, and I'll get rid of it here. Edit. Cut. Okay, so here's my age and my blood pressure. I'm going to go into the variable view and just make sure the names on these variables make some sense. This is age. This I'll call BP. And we know, and we're going to spend some time on this on Monday and Wednesday, coding this data, working with this data in SPSS. We know that our variable name has to start with a letter, can only be letters and numbers, no special characters, and can't have any spaces in it. So it's going to be, we can't just put blood pressure with a space in it and expect that to work here, but we would want it to look like English when we created charts and graphs. So I'm going to call this age for the variable name, blood pressure for the variable name, and in the label area, I'm going to tell it that this represents the age of subject. And in this area here, I'm going to tell it under the label that this represents the blood pressure. And you might even want to be more specific, systolic blood pressure, or just diastolic blood pressure, and so on. Okay, and both of these are numeric. Oops, excuse me. but actually I have to tell it that this is a numerical variable. Probably it defaulted to string because it had age at the top there before I took it out. Okay, probably wouldn't have done that if I had just copied over the numbers. And in here I have to tell it it's a scalar variable. Again, on Monday and Tuesday, we'll actually go through this. We'll create variables. We'll transform them. We'll calculate variables from other data and so on. So I think it's worth Monday and Wednesday is going to be worth spending some time with this and sitting down at these workstations and you guys getting some hands-on time. By the way, if you want to come both days, by all means, show up on both days. You only require you to show up on one. Don't have to tell me in advance, but it wouldn't hurt to come both days because you get a chance to play with the SPSS a bit more. So let me go back to the data view. Okay, so as I said before, the first thing I might want to look at to see if there's an association is I might want to plot this graphically to understand how well that this works. So I'm going to open a graph. There's a number of different graphing tools in here. I use legacy because I am a legacy. So scatter dot, simple scatter dot. Okay, and since again, I'm not worried about as far as this is concerned, correlation, I'm not worried about which one is causing the other, even if either one of them is causing them at all. I'm only interested in seeing if there's an association at this stage. So it doesn't matter which one I call the x-axis and the y-axis right now. When we get into regression, it will make a difference. You can put in titles and dress up the graph a little bit as well if you want to. So I'm going to click OK. And I'm going to look at our output, and in our output, it looks like there's a pretty good correlation between these two. Looks like there's a good association. And I'm not going to bother to draw that line right now because I'm going to get to that when we start to talk about regression. So I'm just going to leave it like that and say, gee, it looks like there's a positive correlation here. Anybody want to guess at what the R value is going to be here based on what you've seen so far? I like that too. 0.85 sounds good to me. Okay, and do you think it's going to be significant? Better than 0.05? I don't know, but it's a decent sample size, and it looks pretty close. Yeah, it's close to one. So yeah, we're about to find out. So let's take a look at this. So now, if I want to actually calculate that Pearson's correlation, I'm going to go to Analyze. I'm going to go to Correlate, Bivariate, two variables. I'm going to put the two of them in here. Okay, and also it's going to be a positive number, as we know. And I'm going to go ahead and say OK. Yeah, let's take a look at that table. Pretty close, 0.821, right? And what about the probability of being wrong if we reject the null hypothesis that there's no association? No, it looks like statistically this result is statistically significant. Right? So basically what I've seen here is that there's a strong, right? It's closer to 1 than it is, a lot closer to 1 than it is 0, a strong positive correlation. As age goes up, blood pressure goes up, or as blood pressure goes up, age goes up, whatever the association is, whatever the causality is there, right? We're not looking at that yet, right? Then as one goes up, the other goes up as well, okay? So now let's think about the next step here. Let's think about quantifying this, right? Wouldn't it be nice to be able to draw a line which best fits all this data, a single straight line, right? That best fits all this data. Anybody remember what the formula for a straight line is? How about you guys online? Yes, you will have this available on YouTube. It's a formula for straight line. I am recording, right? Oh, good. You scared me for a second there when you said that, Vicky. Next week's coding. What's next week? What do you mean coding? I'm not sure I understand.
The class on Monday.
Oh yeah, well a lot of it will be online. I can't swear all the part where we review multiple regression for sure, but as much as I can put online, some of it will be I'm going to walk around and look over people, have people work here, and do the statistics with these databases, and walk around and kind of like kibbutz a little bit. I don't know anybody use that term anymore. Kibbutz, right? Kibbutz used to be kibbutz is I guess it's not German. It's Yiddish, I think, right? Kibbutz. Kibbutz is a term that means kind of like like stick your nose in and get involved and stuff like that. Sometimes where it's not wanted, and it was a common thing when you're talking about like like watching somebody play poker or play or bridge especially. Like somebody would like look over and comment. Uh, Right. So I'm going to do a bit of that. So you may not be able to see that because I'll be walking around, but the rest, but yeah, for the most part, I will be going over I will be doing quite a bit of this. But hopefully I'm hoping you get here for one of those 2 days. So you get a chance to, practice this stuff. So at any rate, so now we want to quantify this. We want to create a line which best fits this. And by best fits, we're going to talk about something that we mean best fits this in terms of least squares. In other words, that if we put this line in here and we look at the difference between the x value and the y value, that difference, the square of that difference, balances out on both sides of the line, that it's equal on both sides of the line, and it's the smallest possible number on both sides of the line. So it's not this, it's not this, right? This, you might be able to draw a least squares line, which goes right through the middle here, like horizontally, where it would balance out. But those spaces, those distances are going to be enormous, right? So it's going to be a big number. But if you draw a line here that goes up here and goes in between them, then the distances are the smallest that they can possibly be and still be a straight line. Well, now, let me get back. What's the formula for a straight line? No, just a regular formula for a straight line. Oh, no, I shouldn't have done that. I don't need that. Let me get rid of that. Okay. The formula for a straight line, let me go to Notebook. Unfortunately, I don't have my graphics tablet here, so this is going to be even a little sloppier than it normally is. The formula for a straight line is y is equal to, this is the mathematical formula, mx plus b, right? What's y and x? Y and x are the two values for the x and the y axis, right? So those are going to represent the point. Now, what is m? M is a number that represents the slope of the line. For instance, this line has a slope, goes for every 2 units it goes across, it goes 2 units up. This has a slope, change in y over change in x. It has a slope that's equal to 2 over 2. So the slope is 1, right? This line goes up 1 for every 2 it goes across. So its slope is 1/2, right? So that number represents the slope of the line. What about b? Anybody remember what b is? Whoops. Let me give you a hint. Let me give you a hint on that. If I were to take this formula, y is equal to mx plus b, right? If the value of x, right? This is the x-axis, this is the y-axis. If the value of x, in other words, right here where x is 0, if the value of x is 0, this is 0. So what is y equal to? Y is equal to the value of this formula where it crosses the x-axis. That's the y-intercept. So if I know the y-intercept and I know the slope, I can draw that line. So everything you need to know to draw a line is in that formula. Now, in statistics, they like to do everything a little bit differently than the rest of the world. So instead of this, we might refer to this as f of x, function of x, or y if you want, is equal to I may get this wrong. I'm having a senior moment here. A plus bx, okay, where b or beta is the slope and a is the y-intercept. I'm thinking it could be b and ax, but it doesn't matter. These two formulas are really the same thing, right? Y is equal to the y-intercept plus the slope times the x value. Okay, so if we have that formula over here, we have a line that describes the best gives us the best relationship between blood pressure and age. Not all relationships will fit that kind of line. Some relationships might look like this. Okay, what kind of relationship is this? That relationship is what we call exponential. In other words, as the x value goes up, the value of y is squared, right? It's an exponential. It's not a straight line relationship, right? So this is only for linear relationships, straight line relationships. But in something like this, there are a lot of types of variables, numerical variables that exhibit a linear relationship. Now, the other thing is that there are tricks you can do to take a non-linear relationship and turn it into a linear relationship. For you guys that have taken a little bit more math, if you take the log of both of these things, you get the log of x is equal to 2 times the log of y, right? And that's a straight line, right? That's a straight line relationship, right? But we're not going to get it. We don't have to worry about that stuff for now, okay? So you don't have to deal with that. But there are tricks. So you can't apply this to every relationship, but to the ones that exhibit a linear relationship, there's a lot of stuff we can do with them with simple linear correlation and regression. And there's many variables that will fit this description. Good. Why I see some people are doing that right. Oh, excellent. Thank you very much, Christine. Okay. So, and somebody that remembers their algebra. Thank you. It's a miracle. So, at any rate, that's where we are. That's where we are so far. We want to describe this a little bit better. So that's where regression comes in. In regression, we are going to redraw this scatter dot plot, right? Except we're going to put the predicting variable, the independent variable, the predictor variable on the x-axis, and we're going to put the dependent variable or the result variable on the y-axis, x and the y-axis. Okay, so let's do that. Okay, I'm going to go up here now to analyze. And instead of going to, well, I'm going to do correlate first. We did correlate, I guess, right? We got that, yes. Instead of going to correlate, I'm going to go to regression. And then I'm going to go down here to, of course, linear regression. Okay, and in this case, I'm going to put the dependent variable first. The dependent variable is the one that depends on the value of the other one. The other one is the independent variable. It's the one that determines the value of the dependent variable. So let's see. Does blood pressure determine a person's age? No, I don't think so, right? It's age that might determine a person's blood pressure. So the independent variable is the age of the subject. The dependent variable is the blood pressure of the subject. Okay, so I can click on this, get all sorts of statistics and stuff like that. But I think basically for what we need right now, I think we're okay. The plots are there to give us various different analyses of the data and the way it agrees with this prediction and the ways that it might not agree with this prediction. But for right now, all I'm interested in is demonstrating this association, number one, demonstrating how strong the association, number two, is, and maybe even using that line to help me out to do a few things. I'm going to click OK. Okay, let's see what our result is. I did an analysis of variance. This is actually a test to see if there's an association between the two of them. It's a significant number, okay? And we also have for our age of subject is also a significant number. So it suggests that that there is an association between the two of them. I wouldn't worry about the 0.410 for the constant right now. I'm going to explain what that constant is shortly. Okay, and the constant is a little less important than some of this other stuff is. And we'll talk about a reason for that. Okay, so the first thing we see up here is the R value. It's just repeated the correlation that we calculated before. 0.821 is the same thing that we just calculated up here, right? The Pearson's correlation. It took that number and it squared that number, 0.674. That's significant to us. We'll get back to that in a second. Okay, down here, it did an analysis of variance to determine whether there is a reason to think that there is an association here and found a p-value. And then it gave us a special table called coefficients. the things that we're interested in here is the first column here, the unstandardized coefficients. So if you look underneath here, B, if you look underneath here, the age of the subject here, this number here represents the slope of this line. The slope of this line is 1.762. The second part of this column, the constant represents the y-intercept. So what did we get from here? We got two things. We got several things, actually. First thing I got is that R is equal to 0.82. I'm just going to 0.82 because it's really hard for me to write here. R squared is equal to 0.674. Okay, so next thing I found out is, and this is significance. So what does this tell me? It tells me that there's a strong positive correlation between age and blood pressure. Okay, well, R squared, why am I interested in the R squared? Get back to that in a second, as I said before. Now, the coefficients part of this thing tells me that the relationship is Y is equal. I like to use mathematical notation, but you could use it the other way around too. In fact, the second half I'm going to do, as you would see it in your textbook most likely, Y, f of x or Y, which is the blood pressure, is equal to the y-intercept, I'll call that B, plus or minus, depending on the sign, the slope times x, okay, which in this case is the age. So what is B? Y, actually, let me undo that. I'll actually add these values. Blood pressure is equal to 17.5. I'll never be able to write all this. I'm scratching on the trackpad here. Plus or minus, let's see, it's a plus or a minus. It's a positive plus 1.76. I'll call that 1.76. I'm going to call it 1.8 just to make this go a little bit quicker. Plus 1.8 times age, our variable for age. Pretty interesting now, right? Now we have a formula which describes the relationship between age and blood pressure. Okay, I'm going to double click on this. Actually, I'm going to redo that chart. I'm going to redo it so that age is on the bottom. Okay, remember when we looked at correlation, we didn't care what direction we went. And also notice that if you reverse these two for correlation, it doesn't matter which one you have on which side. If it's a negative correlation, it will stay a negative correlation. If it's a positive correlation, it will stay a positive correlation. Analyze. I'm going to go to graph, legacy dialogues. Oops, graph, legacy dialogues. Scatter dot. Okay, define. And this time I'm going to move these the opposite way. Whoops, didn't manage to do that right. Okay, blood pressure is going to go into the y-axis, and the age of subject is going to go to the x-axis. I'll click OK, and you'll notice I did that little trick last time. I'll double-click on it to bring up the editing menu, and I'll tell it to create a best fit line, which it does. And notice it created the best fit line, and it plugged in the value. It gave us r squared equals 0.674, and it gave us the value for this line. Now, what is the value of that equation? The value of that equation is that I know now that for every year you age, on average, your blood pressure will go up 1.76 points. Well, why is that important? Well, now this becomes a little bit more predictable. We can see the association between age and blood pressure, and we can understand the effect of advancing age on blood pressure a little bit better. Well, this is kind of a made-up example. But now let's look at this in terms of the amount of sugar that you consume in a day, and maybe maybe you're looking at your insulin sensitivity, and the amount of sugar you increase in a day, your insulin sensitivity increases. You can see, for instance, how much cutting back on a certain amount of sugar per day is going to affect your insulin sensitivity for most people. Well, why is that interesting? Well, because it'll help you set a limit to suggest. In other words, you may find that, gee, it's at an acceptable level if you permit people to drink 7 cans of Coke a day, right? Or maybe that's too much. You need to limit it to 2 cans of Coke a day or something like that, right? It gives you a window on what the relationship between these two is so you can make adjustments based on that. The other thing it allows you to do is, for instance, let's say that you needed $1,000 instrument to measure blood pressure, right? And a person came in. This is really an outlandish thought, but a person comes in and they tell you they're 52 years old, 49 years old, and you say, okay, I can't measure your blood pressure, but for our purposes, I'm going to assume that it is, and you go up to the line and say, oh, it's about 105, right? So what if this were diet? What if this was sugar consumption and insulin sensitivity? Well, you're a person that drinks 3 Cokes a day, so I'll go over here, and I think your insulin sensitivity is going to be about this amount, right? So you can make judgments based on that. You can make predictions based on it. These are kind of like weird kind of associations. So blood pressure shouldn't be on the x-axis. It should be on the y-axis. In this case, I'm sorry, yes, it should be on the y-axis because it's the one that we're predicting based on the age. The age is the independent variable. The blood pressure is the dependent variable. It depends on the value of age, right? Wouldn't make sense the other way around, exactly. So at any rate, so I now have a formula that represents that. Not only that, now I have something else which is real handy as well. Remember that 0.674 that we looked at up there, that R square? That R square represents the percentage of variability in these two values that's determined by the age of the age of the subject. In other words, if this were real data, 67% of the variability in blood pressure is predicted by your age. Okay? Well, now I might analyze something else, like maybe the amount of sugar that you consume. Maybe 10% of the variability of uh, 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 your blood pressure is based on how much sugar you consume. So you can examine which which independent variables, which things have the largest effect on the variable that you're interested in, the dependent variable you're interested in, what causes your blood pressure to be higher, right? So this R square gives you a handle on how much this influences that. Now, if R square had been 0.10, 10%, we would have said, oh, it's very interesting that there's an association there, but it only affects 10% of the variability between of blood pressure in individuals, right? So, gee, maybe we're saying to ourselves now, maybe that's not the most important factor. Maybe there's some other factor we haven't examined which is more important. So that's why linear regression is so important. That's why regression is so important because it allows us to evaluate, number one, how good a correlation there is between two variables, two numerical variables. It allows us to quantify it so we can use it predictively, and it allows us to examine how much one variable can account for changes in the other variable, that R square value. It's really important stuff when we're dealing with numerical variables, really stuff that will help us out. Okay, so I'm going to suggest that we break at this point. You guys watch the lecture. We'll do that here also. And we come back at about 7:30. Okay, and we pick this up and we work on those examples again. Do you have any questions before we cut out? You have some other data sets that I have on Blackboard that we're going to play around with as well. Any questions, guys? Nope. Okay, so take a look at the lecture. The PowerPoint's on there as well. And we'll be back shortly. Bye.